So let me thank Florian and Nikhil for the invitation to tell you about some of our work in Durham on ultracold molecules. So one of the topics we're going to cover is coherent superpositions of ultracold molecules, and I hope I managed to put myself in a coherent superposition of that monitor and this monitor. We'll see how it goes. Okay. So why might you be interested in ultracold molecules? Actually, perhaps before I start, I should say I understand you're mostly interested in clocks, and so I've tried to make this talk as accessible as possible, but I'm no doubt going to fail. And at that point, please interrupt me and ask questions, right? I think there's no need to wait until the end if there's something that's unclear. So please just ask away. So why might one be interested in ultracold polar molecules? There's a number of reasons. I mean, first of all, molecules are really important in the area of fundamental physics and precision tests of beyond standard model physics, for example. That's illustrated by this image from the ACME collaboration, which is one of the experiments using probing beyond standard model physics through measurements of the electron-electric dipole moment. If we can cool molecules to ultracold temperatures, we can also start to learn about chemical processes, but in a quantum state way. So there are people who are interested in ultracold chemistry of molecules. They've been proposed as one of the platforms to do quantum computation, and closely related to that is the idea of doing quantum simulation of many body type models. And I think my interest lies more to the right of this slide, but as you get older, I kind of realize that probably research into these three areas is important because it will improve our ability to do the precision measurements if we can get full quantum control over molecules for those precision tests. So what is it about molecules that gives this richness? So many of the applications stem from the internal structure of the molecule, which is a lot richer than an atom. And I think a lot of you like atoms because they're simple. You have a nice isolated two-level system. It's a good clock, for example. And the molecule is much richer. And in particular, it has this rotational degree of freedom. So even if I have a simple diatomic molecule, just two atoms, they can now rotate around one another. And that gives a new degree of freedom. And these rotational states are very long-lived. And there's a ladder of them. So there's essentially a huge resource of quantum states that one could manipulate. And if you have a polar molecule, like it has a molecule frame dipole moment, then you can couple those rotational states with microwave fields for very strong coupling. Okay, so we can begin to imagine that we might use some of these states to encode spins or qubits in some kind of quantum simulation or quantum computation. And the fact that there's many of these states actually is a very interesting prospect for the area of synthetic dimensions, where you encode many, many levels in the internal space of the particle. The additional degree of freedom that molecules give you is this access to long-range interactions, which at some level is a kind of holy grail of ultracold physics, right? Isolated atoms are very nice, but in many applications, you'd actually like to be able to get them to talk. And one way to do that is through dipole-dipole interactions. And so in the molecule, that can take one of two forms. It can be a spin exchange interaction, okay, which is basically just because there are transition dipole moments between these rotational levels, then spins can hop between neighboring molecules. Or we can apply an electric field to the experiment and orient the molecule in the lab frame, and that produces lab frame dipole moments as a function of the electric field, and those are all very controllable. So what I want to convince you is if we could build a system where we have these molecules arranged in either an optical lattice or an array of tweezers, that's a very rich system for exploring quantum physics because we have these long-range interactions and these many internal states. And so you can think of this system as either an array of qubits or an array of spins for quantum computation or for quantum simulation, more or less the same. And the two interactions I've already described give you what's known as this XXZ Hamiltonian, which is kind of a prototypic model of quantum magnetism. Okay, and these two interactions compete with one another. They can correlate and entangle spins in this system, and that's the basis for this quantum simulation. And they're highly tunable. So this plot illustrates that if I change this external field, I can control the ratio of these interactions. And the same interactions can be used to engineer quantum fields. So where is the field at? Well, actually, as I'll show, it's actually quite hard to see these interactions. But they were first observed back in 2013 in Junyi's group in Jilla using KRB. And I don't have time to explain, but the spin exchange interaction is signified by this oscillation in this Ramsey contrast in this plot. That was the first observation of spin exchange interactions in multiple lattice. Okay. More recently, just last year, Wasim Bakker has now done this same experiment, but in a quantum gas microscope, where you have individual resolution of individual molecules. At the same time, people have been pushing on the quantum computation, and just very recently, these two papers came out in Science. This is using calcium fluoride molecules in optical tweezers. And again, it's the same kind of experiment. You put them close together in optical tweezers and look at this spin exchange interaction. But in this case, they're using it to perform a quantum gate. So they're entangling a pair of molecules via this spin exchange. And a shameless plug of a review that we've just put on the archive. If you want to learn more about these opportunities, I point you to this statement, where we kind of summarize that. So in Durham, I have 3 experiments all working with the same molecule. And they're simply, one experiment works with bulk gases. This is molecules in a simple optical dipole trap. That's the oldest experiment. And then we have 2 new experiments. One assembles molecules in optical tweezers, which I'll explain to you what that involves. And then the more complicated one is to actually put molecules into a quantum gas microscope and be able to image individual molecules in optical lattices. And the molecule that we work with is rubidium cesium, okay, which is perhaps doesn't spring out to you as, oh, that's a molecule I know. But I'll explain how we make it. We first made it about 10 years ago, in 2014. And since then, I think it's fair to say that we've been learning how to control this molecule on this quest for full quantum control. Okay, so maybe I say a few words about what I mean. What would we like? What ingredients would we like in terms of full quantum control? And it may be similar to many of your experiments. And it's nicely illustrated with the atomic quantum gas microscopes. You're familiar with these, where you can put your atoms into an optical lattice, where you can image them with a high resolution objective. And you can use the same objective to go in and address individual particles in this lattice and write your favorite distribution of atoms. So what does this entail? So we'd like to be able to confine the particles in arbitrary traps, arrays. We want motional control. And I'm going to specify that we actually want to be able to resolve the quantum states in the trap. We really want to prepare particles in the lowest motional quantum state. We want coherent control of the internal states, but not just changing the internal state. We'd like to be able to create coherent superpositions. And we'd like to control the interactions, in particular dipole-dipole interactions, but also collisions. I won't say anything more about collisions today. It's complicated with molecules, but we're learning how to control them. And of course, we'd like to do all of this at a single particle level. Okay, so it's quite an ambitious list of things we'd like to be able to do. But what I hope to show you is that we've more or less ticked all of these off. Unfortunately, not in the same experiment yet, but we're getting there. So the plan today is to tell you how we make molecules, just to give some background. And then I'm going to tell you some new experiments on assembling molecules in optical tweezers and the kind of things we can do there to control them. And then how we engineer coherences, which is important to see dipolar interactions. And then, if I have time, to board with me, I'll tell you a little bit about some experiments to make stronger interactions using Rydberg atoms. So how do you make ultra-cold molecules? Okay, so there are two methods that are used widely. The first is, well, let's say, I'll talk about this one, direct laser cooling of molecules, which for a long time was thought to be not possible, but then it was discovered there's a class of molecules that have highly diagonal Frank-Condon factors, which basically means you can do the standard laser cooling techniques, but with only a handful of repump lasers rather than an infinite number. And the other technique, which the one I use, is to not worry about all of that complexity, but just use atomic cooling, prepare ultra-cold atoms, and then bond them together. Harness everything we can do in atomic physics, but just turn it into a molecule, the last stage. Okay, so how does this work? So first of all, you have to get your cold atoms. I'm not going to explain how we did that in great detail, but let's assume we have a mixture of ultra-cold atoms. The challenge then is to go from these free atoms all the way to this ground state of the molecule. Okay, and the binding energy for rubidium cesium here is about 4,000 wave numbers, or 120 terahertz or so in frequency units. So let's zoom in. We know, hopefully it's familiar to you, that we have things called Feshbach resonances, and they arise because if we look at the very near threshold bound states of this molecule, so notice the energy scale here is a few megahertz, and the energy scale on this diagram is 120 terahertz. So we're really looking at the last little sliver of binding energy. So we have these near threshold bound states, which come up and cross the atomic threshold. And when they do, they give rise to what's called a Feshbach resonance. And we can use that resonance if we sweep the magnetic field across such a resonance, the right speed, couple into one of these weakly bound states. This is what we do in rubidium cesium. We start here, we sweep, and we couple into this red state, and then we actually go down to the next resonance and go into this more deeply bound state. And that's how we prepare weakly bound molecules. Okay? And you can just about see this little signature of cesium atoms and rubidium atoms down here compared to these big clouds. That's the 4,000 or so molecules that we've made in this magnetoassociation process. Okay. Those molecules are not so useful because they have no dipole moment. They're so weakly bound, big floppy molecule. But they have wave function at short range. That's their useful property. And we use that in the next step to transfer the molecule from this very weakly bound state all the way to the bound state using two optical photons in a Stirac process. And we take care. So when we go down there, we look at the vibrational ground state of the molecule. So that's easy to resolve. That's terahertz separations. We go to the rotational ground state of the molecule, separated by gigahertz. And you look very, very carefully. The molecule has hyperfine structure, which looks something like this. The rubidium cesium has 32 hyperfine states in the ground state. And we have to resolve that, but we do, and we go to the absolute ground state of the molecule. We do the experiment at about 180 Gauss, and we go to this +5 state. So the molecule is prepared in the rho vibrational and the hyperfine bound state with Stirac. How does Stirac work? If you're not familiar with it, it's this coherent adiabatic evolution of a dark state, which goes from being the Feshbach state to the ground state. And you will read in the literature about this counterintuitive pull sequence. So we first turn on this orange photon, which prepares the dark state as the Feshbach state. And then as we ramp that off, we ramp on this pump photon, and that gives the coherent evolution of the dark state from the Feshbach all the way to the ground state. Crucially, without ever populating, if you do it properly, this excited state. You don't want to go up there because the excited state will decay all kinds of places. But you don't want. What you see in the experiment is all your molecules go away because they've gone to the ground state. And so an important point in these experiments is we don't detect the ground state molecules directly. We reverse the Dirac. Okay. So we do that full sequence again and transfer the molecules back, break them apart, and look at the atoms that result. And so when you see your signal come back like this, that's when you crack open the champagne and you celebrate. And so this is very efficient. Actually, we have over 90% one-way transfer efficiency. And we're preparing about 4,000 molecules at about a microkelvin. They're actually fairly dense, and so collisions are important in these experiments. And just to reiterate, we're going to this absolute hyperfine ground state, and the Dirac only addresses that state. Okay, so effectively, the Dirac gives a state-sensitive detection of the molecule. So if I was to break these pulses apart and then do an experiment on the molecule, such as driving a microwave transition from n equals 0 to n equals 1, I would see the evidence of driving the transition as a drop in the molecular signal. Okay, because the Dirac is only addressing this particular state. Okay, so that's an overview of how we make the molecule, how we do an experiment on it. Don't know if there are any questions at that point, or I go into optical tweezers. No? It's good. I'm doing a good job or a very, very bad. Very good. So I'm going to tell you about controlling single molecules now. And one of my desirables on my full quantum control list. And how many people are familiar with optical tweezers? Yeah, half or so. So I've put in a slide yesterday for those that don't. So this is a kind of generic optical tweezer setup from this nice review paper in Nature Physics. And the basis of a tweezer is you take a laser beam and you focus it to about a micron. So do a good job at focusing it down as you possibly can. And you can generate arrays of those traps. And you can do it in one of two ways. So in this diagram, one of the arrays comes from a spatial light modulator, liquid crystal spatial light modulator, for example, and that will create a static array of traps. Okay. And then they also have this 2D AOD, acousto-optic deflector, which creates a single trap that you can move around dynamically. So you can use that for reshuffling atoms. And the nice thing is you can detect the atoms by collecting the fluorescence from them using the same lens and just split it off and put it onto a camera. And this was first demonstrated many, many years ago now, 2001. And this shows a nice picture where you're detecting this fluorescence and you see it jump up. And you can see in the image that when it jumps up, you get the fluorescence on that trap. And this is a single atom. So the physics of this is the tap is so tight that you get light-assisted collisions of multiple particles such that you either load 0 or 1 atoms into the trap. Okay. But you can see which traps you loaded, right? And that's the important thing. And so you can take pictures like this of an array and you get this random loading. Okay. But then you can use this dynamic tweezer to go in and shuffle the particles around and then produce the ordered array that you want to do an experiment. And it's become a very powerful platform. Many people are using it and many companies are using it as well. I'm glad this works. This is a very nice example of the looping group, just illustrating the power of this. So what you're seeing here is arrays of atoms being coupled around, and when the circle appeared, so I'm going back. When the circle appears, they do actually an entangling gate between pairs of atoms in this experiment. So, but it gives you an idea of the level of control that you can have in these optical systems. So we want to do that, but actually make a molecule. And so what we do is we load two species, a rubidium atom and a cesium atom, in separate traps. there's a subtle point about this, that then you have to prepare those atoms in the motional ground state of their tweezers. Okay? And we do that using Raman side-bank cooling. And that's necessary because, actually, the theory's been known for a long time. It's only the motional ground state that, when you sweep across a Feshbach resonance, couples into the molecular state. So you have to be prepared in that motional ground state. So then we take these two tweezers, one with the rubidium atom, one with the cesium atom, and we merge them together. And then we do the same steps that I've told you about. We do magnetoassociation and stir up to the ground state, prepare a ground state molecule. And then mostly we reverse that and pull the atoms apart at the end and detect them again in their respective tweezers. And to point out, there was real pioneering work in Kang Ni's group in Harvard on this using sodium cesium. So this is what the experiment looks like. I think compared to many of these experiments, it's remarkably simple. So this is the whole vacuum system. It really is just a mott in a cell and a big lens, right? And through that lens, we put two wavelengths, 817 nanometers, put three wavelengths, but predominantly 817 and 1065, 1066. And these are species-specific traps. And so 817 is repulsive for cesium, but attractive for rubidium. So that allows us to guarantee that we only load rubidium into that trap. We also have this 938, which we use for shuffling around the cesium. And this just illustrates the detection. So again, we collect fluorescence from the atoms and record the counts on the camera. And you see very clear distinction between no atom and one atom in terms of the count. And so that allows you to detect the presence of an atom with exceptionally high fidelity. One of these beams is controlled with an SLM, so you can write your arbitrary pattern, okay? And it's almost obligatory to prepare your local landmark. And so we made the Angel of the North. Not familiar with it, this is a sculpture by Anthony Gormley that sits by the A1. It's about 50 meters across in terms of wingspan. It's a spectacular sculpture. And this is our rendition of it, which is about 50 microns across, made with individual cesium. I don't have time to go into the details, but as I say, we do Raman side-bank cooling. And this actually prepares the rubidium and the cesium atom in the motional ground state of their respective traps. And then we do this careful merging of the two potentials. So we just sweep using one of those AODs, the 817 trap, to overlap with the trap containing cesium. And then we ramp it off. Actually, in the process of this, we found an entirely new way of making molecules, which we failed to come up with a better name than mergo association. But you can ask me about that in the coffee break if you're interested. So this summarizes the molecule creation steps. So we can do magnetoassociation. So this is sweeping across that Feshbach resonance and looking at the efficiency of forming a molecule as a function of this ramp speed. You see we form molecules in somewhere between 50 and 60% of the time. Actually, the magnetoassociation step is almost 100% efficient. What's not 100% efficient is the preparation in the motional ground state. So we're only preparing the molecules in the motional ground state in 50 or 60% of the time. Stirrup efficiency is very good in this. It's 96%. We measure that by giving the molecule a headache by transferring it backwards and forwards on microsecond timescales between the ground state and the Feshbach state. So we do that up to 60 times. And from this decay, you can extract the stirrup efficiency. But the point is, I suppose the summary is, we prepare an atom pair, and around 50% of the time, we convert that atom pair into a ground state molecule. And the important thing is that molecule is predominantly in the motional ground state of the trap. And so we prepared it with motional state control. So that's ticking off one of my full quantum control requirements. We can actually, the tweezers are wonderful, and I want to try and spend a few slides explaining why they're wonderful. So one of the things we can do is error detection. Okay. So this is what I've just described. We create a tweezer array of rubidium and cesium. We make some molecules, but we make them in roughly 50% of the sites, right? So in the sites where we don't, we're still left with an atom pair. So what we can do is use the rubidium tweezer to pull out a rubidium atom from those sites. We try and pull out from all sites, but it only pulls out a rubidium atom if there's an atom pair. And we can then remove the cesium. And see what we're left with is an additional array where the presence of a rubidium atom shows that there wasn't a molecule in the molecule tweezer array. At the end, we, as I said, break apart the molecule and then do post-selection, only looking at those sites where there isn't a rubidium atom in the detection array. So this is a kind of almost like an erasure conversion process that is used in an atom experiment. We can drive microwave transitions. I'm not going to go into too much detail, but it's very easy to go up to n equals 1. It's a spectroscopy shown here of different defined states, different polarizations. We can go up to n equals 2, n equals 3. Actually, in our bulk gas experiment, we've gone up to n equals 6. It's really just limited by how many microwave sources that you can cobble together or afford. So this is this idea of using this as a synthetic dimension. Okay, you can think of these as lattice sites in some synthetic dimension. And the coupling is very strong, it's very coherent, nice to fit these spins in the model. We can do single site addressing. Okay, we'll come on to the fact that these transitions are AC stark shift. So in this experiment, we apply light, 817 light, to certain sites in the array. And then what you see is that the transition, the microwave transition, is shifted on those sites. So if we then just apply a pi pulse on the bare transition, we can flip all the spins off the non-addressed sites in the array. And so in this case, we prepare an array of spin up, spin down, spin up, spin down, spin up. And then if you drive microwave transitions on the global system, you see these oscillating out of phase. Gives an idea of the kind of control you have in this tweezer platform. We can also do multi-state readout. Okay, so one of the challenges of molecules is detecting it, and so it's nice to enhance the way you can do that. So in this experiment, what we do is we're driving microwave transitions between two rotational states. Remember, stirrup is state sensitive. So we perform stirrup and transfer back to atoms, but that only transfers the ground state, the rotational ground state. And then we pull those atoms out and put them in a trap. And then we apply a microwave pi pulse, and any population that was n equals 1, we transfer into the ground state and do stirrup again and pull that atom out into a different trap. Okay. So then at the end, we have the trap which contains cesium. We have a trap for rubidium, which would signify the presence of an n equals 1 molecule, and a trap for rubidium, which signifies the presence of an n equals 0. So in this experiment, then, we are able to do this microwave oscillation, but read out both states of the molecule. So, just to go back to this error detection, so the thing we've just done, just before Christmas, is to use that information to do rearrangement of the molecules. So what this involves is actually just developing the ability to image the atom at high magnetic field, rather than at the end of the sequence. So we can do that now. We can image at the 180 Gauss the rubidium atom, and remember that's showing us where the errors are in our array, and then we can reshuffle the molecular population. And this was just done on a small array, but you see without this rearrangement, we have roughly 40% probability of getting a molecule in any trap. But when we do the rearrangement, we can shuffle molecules to one end, and we're getting close to our detection limit on filling up this array. Of course, what we'd like to do is scale this up and get many more molecules, which actually just means buying bigger lasers, as is often the case. Okay. So that hopefully gives a flavor of the control you can have at the single particle level in terms of manipulating molecules. What I want to talk about is coherences. Okay, so we've been able to drive transitions between rotational states, but I'd like to show you that it's necessary to have coherent superpositions of those states for a lot of the applications, not least to engineer dipolar interactions. So just to go back to the beginning, just to emphasize, yeah, it's nice, so we can create this system now. I think that's fine. But actually, observing dipolar interactions between the particles is still challenging. And why is it challenging? Well, maybe the eagle-eyed spotted. If you look at this plot, which I said this is great, it allows you to control the interactions. Actually, the energy scale goes up to 1 kilohertz. So this is rubidium cesium molecules in a 1064 nanometer lattice. So they're spaced by about half a micron. The dipolar interaction between neighboring sites is of order 1 kilohertz, okay? Which is not very big. And if you were to do it in tweezers separated by 2 microns, that interaction might only be 20 hertz. And many applications require us to engineer a rotational coherence. So if you're going to do a quantum gate or quantum simulation of quantum magnetism, you need rotational coherences, and those coherence times need to be longer than this dipole interaction time set by this interaction energy. And that's hard. Right? And that's actually very hard. And this is a plot that gives you the energy scales involved in these experiments. And of course, the dipolar interaction sits right down the bottom, optimistically at the kilohertz level. And crucially, it's about 200 times smaller than the track light ships that we're using. So what this means is we really have to know and understand and control the optical shifts in the track. Okay? I'm speaking to a clock community, so you understand about controlling optical shifts on clock transitions. It's the same idea here, except now we need to do it on a rotational transition of a molecule. Okay, and why is that hard and why is that complicated? It's because it's a molecule, and everything is hard and complicated. So basically, because even in a simple diatomic molecule, the polarizability of the molecule is different, orthogonal to the bond axis and parallel to the bond axis. And so that means that it's very complicated, and it depends on the polarization of the laser with respect to the molecular frame. And we write it often like this as an isotropic polarizability. And this is the same for all rotational limits. That's fine. Okay, but then there's this anisotropic term, which captures the fact that the polarizabilities are different in the different directions. And this is almost zero for the rotational ground state. And we showed in 2019 that means you can have very long-lived coherences in the rotational ground state. So what we're doing here is preparing a superposition of 2 hyperfine states in the molecule. So the polarizability is basically the same. And you can get coherent superpositions measured in a Ramsey experiment for over 5 seconds. Okay? That's actually limited by collisions that I'm not talking about. The problem in n equals 1 is this anisotropic term mixes the hyperfine structure. Okay, and if you like matrices, you can see that this is in the Mn basis, and this interaction gives both diagonal shifts and also off-diagonal couplings, and it's all controlled by this alpha 2 parameter. If you don't like matrices, like me, if you like the experiment, so this is the experimental measurement of that effect in rubidium cesium. Okay, for 2 different laser polarizations, perpendicular and parallel to the quantization field. these little dots that you can barely see, or each one is a measurement of the microwave transition frequency. And what we're looking at is that transition frequency as a function of the laser intensity. Okay? And you can see this mixing of all the states and avoided crossings, and molecules are very rich. That's what we like to say, right? So this is the rich structure of molecules in evidence. But this causes a problem, right? Because wherever you look on this plot, there's generally a strong intensity dependence to the transition frequency. And a strong intensity dependence to transition frequency means a molecule in a trap sampling different intensities, and then it's going to T-phase. Okay, and that's what limits coherence times. And it all comes from this anisotropic polarized filter. And so I can show you how great this is at T-phasing. So this blue measurement corresponds to varying a superposition with this rotational state. I have a linear shift in the transition frequency, and it dephases in about 100 microseconds for a set of molecules in a trap. We tried to be smart. We went to this avoided crossing, and it definitely improved things, but the timescale is still about 1 millisecond. Okay? So 1 millisecond, but my best case scenario is 1 kilohertz for my dipolar interaction. So this is the problem. Okay. And it's not just rubidium cesium. Right? This is every molecule. And so if you look in the literature, the original KRB experiment where they saw this spin exchange interaction had a 1 millisecond dephasing time. There are all kinds of tricks being played, changing the angle of the polarization and trying to find magic wavelengths. But the record here is 100 milliseconds or so. And it's prompted all kinds of interesting spin echo techniques like this XY8 dynamic decoupling sequence that's used in NMR. So what have we done? So we've actually benefited from a wonderful collaboration with a theorist in the US, Stefana Chigova, who helped us identify a magic wavelength for the rotational transition. And to explain that, I mean, basically what we'd like to do is make this anisotropic polarizability 0. And the understanding, the way you do that is to realize that these two polarizabilities come from different transitions within the molecule, completely different symmetries. And so the idea is you tune your laser that you're trapping the molecule close to one of these transitions, and then you should be able to tune one of the polarizabilities without affecting the other. And you just tune it until it's equal to the other one, and the anisotropic polarizability goes away. Okay. And the transition we choose is this nominally forbidden X to B transition in the molecule at 1146 nanometer. It's weakly mixed with another state, which means it's allowed slightly. And that allows us to control alpha parallel without affecting this alpha curve. And so the idea is to tune alpha 2 to 0 using this. It's a bit of a busy slide, but all this is showing is that same picture again. Now, what happens is you tune the laser frequency through the vibrational levels outside of the state. You get a pole every time you hit the transition, but you see alpha parallel tunes smoothly between these poles, so as alpha curve is unaffected, and there's this magic wavelength here. This is just converting it into polarizabilities of the ground state alpha 0 and the first rotational state alpha 1, and this is the scenario where we get a magic wavelength, which corresponds to the two potentials looking like this, as you know. Okay. The good news is this magic wavelength is detuned by about 180 gigahertz or so, which doesn't sound much, except the transition line is about 10 kilohertz. So this is actually a far detuned magic wavelength. If you translate it to rubidium, it's about 300 nanometers detuning from a D line in rubidium. So we can do the spectroscopy. So this is looking at the light shift of the microwave transition as a function of that laser detuning, seeing the vibrational poles associated with the excited states. And just above each vibrational pole is this magic wavelength. To measure the magic wavelength more precisely, we actually do a Ramsey measurement and look at the contrast of the Ramsey sequence as a function of laser detuning. And so you map out fringes. Now this detuning is on the sub-gigahertz level from the magic wavelength. And we've done that for a whole variety of superpositions in the molecule for reasons that will become evident. But let's look at this red curve. This is a superposition of 0 and 1. So just this pair here. And we look at the contrast as a function of the laser wavelength. And we see at about 180 something gigahertz, we get a peak in the contrast where we're exactly magic for that pair of states. Okay. It's slightly different for different pairs of states, and these are other combinations within this rotational manifold, but they're all within about 1 gigahertz for several of each other. So let's see what kind of coherence we get. So this is now looking at the fringe contrast as a function of time, and it's for a 0-2 superposition. Okay, so we've used a 2-photon microwave to prepare a superposition of n equals 0 and n equals 2. And the reason we've done that is there's no directly allowed transition dipole moment between the two molecules, which is important. And when we did this, we saw a bare coherence time of about 0.8 seconds, straight off the bat. Okay? And with a simple pi pulse spin echo in the middle, we measure, we see no loss in coherence over the measurement time of the experiment. And this is completely limited. We understand this. It's limited by how well we were locking the laser. If we lock the laser better, its bare coherence just gets longer and longer. So this is 1,000 times better than we've ever done. And it's also a lot better than anybody's ever done in a molecule. And crucially, it's long enough to see dipolar interactions, which is kind of, for about 10 years, I've been saying molecules are great because you can do dipolar interactions. And now we have the possibility of seeing them. So how do we see them? We use a rotational superposition that has an allowed transition. Okay. So this is 0-2, no directly allowed transition. If we do 0-1, then what we actually create in that superposition is an oscillating dipole. For preparing a superposition of n equals 0 and n equals 1, my molecules become an array of oscillating dipoles. This is a thermal gas. You said this is a bulk gas experiment. So this is a oscillating dipoles moving around the track randomly. What does that lead to? Dephasing because of the dipolar interaction. Okay. So there we measure a much shorter coherence time, and we see this coherence decay away because of dipolar interaction. And we can do that, we can change the dipolar strength, right? The reason I have lots of superpositions in that diagram is because each one of those superpositions has a different transition dipole moment, which leads to oscillating dipoles with different dipolar strengths. So then you can measure the coherence time as a function of the dipolar strength, and the bigger dipoles decay more rapidly in their coherence, as you'd expect, because of this interaction. And you can invert that and show that, yes, you get the expected behavior that the coherence time scales inversely with the interaction strength. So finally, we're able to see dipolar interactions in a molecular gas because of this magic wavelength. And the next step is to put these into arrays. Actually, we're currently working on adding the magic wavelength to the tweezers so that we can see very long coherence between pairs. Okay, I don't know how I'm doing for time. Probably okay. No, you don't know, so that's fine. So I just wanted to have a short outlook. It won't be very long. You're like me, you're all physicists and you're greedy for even better things, right? And so what we'd like is stronger interactions. I'm sure you're aware that molecules are not the only dipolar system in the game. There's wonderful experiments on highly magnetic atoms, such as dysprosium and erbium, using magnetic dipolar interactions. And there's fabulous experiments on Rydberg atoms. And Rydberg atoms are very different. There you're exciting to a high principal quantum number, and this gives transition dipole moments which are killer divide, huge. But of course, that comes at the cost of the Rydberg lifetime is of order 100 microseconds or so. So we tend to think of these as fixed dipoles. You can do a lot of quantum gates and simulations, but all the particles have to be fixed on the interaction time. Whereas here, in these two systems, the molecules and the magnetic atoms are mobile. So we've started some experiments to say, well, can we take the best of these two systems, all the good things, and leverage them to make a better experiment in a hybrid approach? And so, actually, we're not the first people to think about this. When you look in the literature, there's many proposals going back quite a few years. And the idea is to use the Rydberg atom, for example, to mediate interactions between molecules, leverage that strong interaction. And one of the applications might be to do non-destructive readout via the Rydberg atom. And so leave your molecule intact, but measure its presence by the Rydberg atom. There's new physics in forming what's called giant polyatomic molecules. And there have been proposals on cooling molecules using Rydberg atoms. So there's a lot of motivation, I think, studying this area. So we started a collaboration with these wonderful people. And the idea of the experiment was to place an atom close to a molecule, or we have that already in the tweezers, and then do a Rydberg excitation of the atom. And if you do that get the atom and molecule close enough, they actually have this charged dipole interaction, where effectively the Rydberg electron is getting close enough to the molecule that its electric field is polarizing the molecule, causing an interaction. What does close enough mean? Well, it actually means getting the molecule more or less into the Rydberg orbit, which for, I think this is 52S in rubidium, is at about 300 nanometers or so. So if I can put my molecule 300 nanometers away from my atom, then I should see a sudden change in the interaction energy, the sudden turn on, and get megahertz shifts of the Rydberg transition due to the presence of the molecule. In short story, I was going to say, how do we do that? I'll just cut to the chase. We can do that. So this is driving the Rydberg transition now in the atom. We see oscillations to the Rydberg manifold and back to the ground state without a molecule. And then when we do it in the presence of a molecule, 300 nanometers away, then we blockade that Rydberg transition. So this is Rydberg blockade, but now due to the interaction with a molecule, not due to interaction with another Rydberg atom. And so we suppress this excitation of the atom. We can do that spectroscopically. So let's do that. So this is at a separation of 700 nanometers. And there's no interaction at that distance. So that's just the bare atom. When I have a molecule present, it looks exactly the same. But if I tune the separation down to 300 nanometers, then of course it looks the same when the molecule is not there, but then I get this suppression when the molecule is present. Okay? So already this would allow us to do a non-destructive detection of the presence of the molecule by interrogating the atom. What we're working towards, I said we were greedy, we want even stronger interactions. And the way to make the interactions really strong is to find a pair of energy levels in the Rydberg atom where the spacing exactly matches the rotational splitting of the molecule. So then you make a resonant dipolar coupling between the two systems, and that just scales as the molecular dipole times the atomic dipole. So I take my 1 dpi in the molecule and I multiply it by 10,000 dpi in the Rydberg atom. And there are proposals to use this by putting the Rydberg atom between two molecules. I can entangle the molecules just by driving a transition in the Rydberg atom. This is just a slide to say, is this possible? And the answer is yes, it's possible in many different ways. So what this is showing is these are the rotational energy levels in the molecule, the transition frequencies rather. And these blue and red and green are transitions in the Rydberg atom as a function of principal quantum number for rubidium and cesium. So the reason we went up to n equals 3 before in the microwave transitions in tweezers is because n equals 3 is then resonant with this 83 transition in rubidium, which is the one we're targeting at the moment. Okay. So I should stop there because I have taken more time than I should have. So I hope I've convinced you that we're well on the way to getting full quantum control of molecules. We can have long-lived coherence in nuclear spins, but also in rotational states now, and C dipolar interactions. And at the same time, we can do this at the individual particle level, assemble individual molecules, rearrange them, dress individual molecules, read out multiple states, and so on. So just, I should acknowledge, it's interesting, Bill is hiding. The two postdocs who have really led these experiments in my group, and we've benefited from many fruitful collaborations with people around the world, too many to go through. And if you are looking for a new direction to your career, this is Durham. It's always sunny, just like that. And so we're always looking for people to come and join these experiments. So thank you.
We can still take some questions. Yeah, please.
Fantastic progress, Simon.
Thank you.
As I understand it, you're limited. Your tweezer spacing when you're actually holding two separate tissues is limited to a few hundred nanometers. So you can actually merge tweezers. So what is it that's limiting the?
So in the
smaller spacing that you can.
Yeah. So the way we get 300 nanometers. So what limits it is collisions. If the particles actually spill into the same trap, if a molecule's involved, then they collide and you get loss. And so the trick for the Rydberg atom is we use the potentials. Maybe I have some slide. The rubidium's in this 817 potential, which is very weak for the molecule. And conversely, the molecule's in 1060 something, which is actually quite weak for rubidium. So it's using the trick of having species-specific potentials to push the particles close together. And we can get down to about 250 nanometers with that approach, and then the atom spills into the molecule trap when they collide, and that's it. Yeah, so that's partly the limitation with the tweezers. I think there's experiments, and this is somewhere where I'd like to go, is to combine the tweezers with lattices. Because putting two molecules together in the magic wavelength is harder, because obviously they're experiencing exactly the same polarizability, and so they spill more quickly. But if you have a lattice, a magic lattice, for example, then you could get to lambda over 2 very easily. So that's, and I think at half a micron, the interaction is strong enough to do interesting things. Yeah.
Any more questions? Yeah.
Thank you for the nice presentation. How many tweezers do you have?
At the moment, we start with only 10 or 12 of each of the rubidium and cesium, and that's just laser power. As laser power and money. It's when you start these experiments, you don't have infinite amounts of money. So
Are you measure the fidelity as well?
Sorry?
The fidelity.
The fidelity of what? Sorry. You mean driving the transition? We haven't done any measurements of good doing kind of randomized benchmarking or anything like that. We haven't done that. So what we did in the paper on robust storage qubits was really just to identify the conditions in which you could get these super long-lived coherences. And if you put in the numbers, the coherence time theoretically is about 2,000 seconds. So that would allow you to do very slow driving. It's not necessarily what you want, but the figure of merit is always coherence time to gate speed. Yeah.
Oh, okay, yeah.
I mean, the naive theory thought could be, I mean, there should be Rydberg states in the molecules as well.
Yeah.
Use them.
Yeah, we have thought about that. There's not very much known about Rydberg excitation of rubidium cesium, whereas rubidium you can just take this software package ARC and you put in the numbers and dial your laser and away you go. Right, so it's leveraging the simplicity of the atom, because in the tweezer platform you have rubidium atoms and cesium atoms anyway. They're there.
To turn off the tweezers when you excite the Rydberg?
No, so we're leaving the tweezer on, and that's how we're detecting the excitation, because of course the tweezer is repulsive for the Rydberg, and so it maps Rydberg excitation onto loss of the atom. So that's effectively how we're doing the detection. Yeah.
Okay, yeah, final one, please.
You mentioned that this dipole-dipole interaction is like 200 times bigger than Stark shift of the dipole traps, in which
Yes.
the molecules
Yeah.
have been confined. Would it be possible to transfer these molecules in a repulsive trap where the atoms sit in minimum intensity area, so that we don't have this Stark shift?
Oh, you mean use a blue detuned
Yes.
trap? Actually, blue detuned traps for molecules are quite tricky. And that's because if you go back and think about the molecular energy levels I showed, it's very easy to be red detuned of all of those, but basically there's just so many transitions when you get up there that being blue detuned is actually very hard. It's not like an atom where you have these huge gaps in the spectrum. Those potentials, which span thousands of wave numbers, are full of transitions. And so it's actually very hard to get blue detuned. Yeah.
Okay. Anyway, Simon is around, so take this opportunity to interact with him if you still have more questions and if you just like to know more about his work. So let's thank Simon once again for his excellent work.